This is part 3 of the 3.2 notes. So far we've been talking about regression lines in general. In this section, we're going to introduce one of our particularly special regression lines, and that is the least squares regression line. There are a few different types of models that you can use, but this one is the one that is most common. In fact, when we see computer outputs like this Minitab output down below, or what your calculator is computing, is that least squares regression line. So the least squares regression line is a special line that tries to minimize the sum of the squares residuals. So I'll put up a visualization of what that looks like, but we're taking the residuals and trying to make as many of those as small as possible. It also passes through the mean point of both x and y. So the mean of x and the mean of y, that's what I've written right here. Just a particular point that it will pass through. So when you're looking at a computer output, you'll see this in your textbook a lot and in different places. The slope is this number here on the bottom. So you'll see that on the left-hand side here, there are a couple different words. One of them is a constant, and one of them is the context. So the miles driven is the context that we've been using with the Ford F-150 problems. That is your x. That is our explanatory variable. So that's the variable that you're going to be on the lookout for. That's going to indicate that your slope is that number. The y-intercept is the constant. So the constant is that number that doesn't change. That's the one without the variable. So that top number is our y-intercept. Another way you can remember that is our equation, our least squares equation is going to be in this format. And the a comes first, that y-intercept comes first. So that y-intercept number, and then the slope comes next. So the slope is the number with our explanatory variable. A couple other things to point out real quickly is that S stands for the standard deviation of residuals. That's what we've been interpreting. And our R squared is this right here. It says R and then SQ. This R squared adjusted, you can just cross that out and ignore that. That one is not going to come into play. Besides using that to get the information for our least squares regression line, you can also use the formulas that are provided down below here. These are also in your AP formula packet. So if you're looking at your formula packet, you can see that we have a couple equations for our least squares regression line. The B is going to give us the equation for our slope. So this is our slope equation. And then we also have an equation for our y-intercept, that A. So that bar over the top of these x's tells us that that is going to be the mean. So when we're calculating the y-intercept, you need to find the mean of x and the mean of y, or those will be provided for you. But you also need the slope. So that b right there, that is our slope value. These s's are the standard deviations of, or standard errors of y and x. So individually, you'll be provided with those. And R is our correlation coefficient. A few things about regression real quickly is that regression, when you switch around the x and the y, so you switch around your explanatory variables, your x, and your response variables, your y, you'll end up with a different line for the slope and y-intercept because it's at a different angle in terms of which one is your explanatory and which one's response. But in fact, you will end up with the exact same correlation and coefficient of determination. That's because those two variables, that when you switch around x and y, they do not impact how they are tabulated. So those are both tabulated using like multiplication. And if you just reverse around the order of multiplication, it doesn't impact that. So that's looking at the relationship between those two, the x and the y. And so if you reverse your x and your y, the correlation and coefficient of determination, so correlation is that r, coefficient of determination is r squared, those will not change. A few more notes, moving on to that next page. Ooh, there it is for me. So we have the least squares regression line is not a complete picture of the relationship between two quantitative variables. If we're looking at two things, we need to also be looking at a scatter plot. If we're just looking at an x and a y, you also need to be looking at the scatter plot, or I should say in addition to the residual plot. So It is not a complete picture. Just looking at the computer output is not enough. You need to look at a scatter plot or a residual plot, probably both. And residual plot. Least squares regression line is not resistant. We'll be taking a look at that in a little bit more detail later on, but a least squares regression line is highly influenced by outliers. So if there's one point that's kind of messing way out there, it can make a huge change on it. And lastly, you should know this one: correlation does not imply causation. Just because there is, some numerical evidence for two things being related does not mean that they are directly related, that there is not a causative relationship. All right, so let's take a look at an example. So this is an example using those means and standard deviation formulas from that other page. So we have the flubber and gizmos. That's the context of this problem. Number one says find the least squares regression line for the data above. So we have our two equations. Our standard deviation equation helps us find B, which is our slope. So we plug in our R, our correlation value. The standard deviation of y and standard deviation of x are provided for us in the problem, with the standard deviation of y going on top and the standard deviation of x going on the bottom. We tabulate that and we end up with 1.2. That's our value of B. Then from there we can take that value, plug that in for A, or plug it in for B, I should say, rather, to find A. So we have the mean of y minus the slope times the mean of x, and we end up with 0.8. So we end up with our final equation where the A is our y-intercept, 0.8 gizmos, and our slope is positive 1.2x. Interpret that slope in context. So this is using that formula from the front sheet. So if you need to look back to that packet, that is perfectly okay. Just kind of as a guide, we're going to be talking about 1x. Whenever we're looking at slope, we're thinking about what happens when x, our explanatory variable, is 1. Whenever we're talking about the y-intercept, that's x is 0. So for every 1 additional gram of flubber, that's our x, our explanatory variable. So for every 1 additional gram of flubber, we predict. That's the key phrase that we use. Anytime we are talking about a model, we need to use that word predict. Gizmo output will increase by 1.2 grams. Because it's a positive, we're looking at an increase. For our third one there, what is the y-intercept interpretation? So 0.8 is the predicted. Once again, we're talking about a model, and models just provide us with predictions. So this line is going to predict gizmo output when we have 0 grams of flubber. So 0.8 is that gizmo number. For our fourth one, interpret the correlation coefficient in context. What is R? R tells us that this is a moderately strong positive linear association. So R is a little bit like stud, not quite all the way. It doesn't include the unusual features. R does not tell us anything about that, but it gives us an indication of the strength of the linearity. So moderately strong positive linear association with context, grams of flubber and gizmo output. For that fifth one down, interpret the coefficient of determination. Coefficient of determination is R squared. How we can compute that is by taking our R value from up above and squaring that. So 0.8 squared is 0.64, and we use the slope of the sign of the slope. So since our slope was positive, this will also be a positive R, and then R squared will obviously be positive. So 64% of the variation in gizmo output can be accounted for by the linear model relating gizmo output to grams of flubber. That is one of our sentences that you need to know, one of our sentences that you need to have kind of in that memory bank. That's 0.7 if you're referring back to earlier in the packet. Continuing on with this particular problem, at the top of the next page, we have predict the number of gizmos you would expect to obtain from 10 grams of flubber. So we're going to plug that back into our equation. So we plug 10 into our equation, and we end up with 12.8. So we predict 12.8 gizmos for 10 grams of flubber. That's the context. For our seventh one, When we have an actual yield of 10 grams of flubber, we end up with 15 gizmos. So what is a residual? Remember that a residual is the actual minus the predicted. So our actual number is 15 gizmos minus our predicted number, 12.8. That produces 2.2. The residual is 2.2 gizmos. So because we predicted fewer than we actually have, this is going to be positive. That is a slight underestimate. We can also use the computer output to get that least squares regression line. So in this particular problem down below, we're looking at a test scenario where a teacher assigns students seat locations for a particular chapter and then gives them a test at the end of the chapter to see does seat location affect their test scores. So we have the residual plot provided for us along with computer output. Whenever we're looking at that computer output, remember that we have our explanatory variable, our x, is going to be on the bottom there. So that is our row, is our explanatory variable. Our response variable is going to be up top here, and that is associated with our y-intercept. So the constant is when you don't have that variable. Just as a quick reminder, we're looking at y equals a plus b to the x. That is our regression equation. So the constant, the one without any variables, is 85.706. The one with the x, one with the variable, is negative 1.117. S here is our standard deviation. R squared is R squared, coefficient of determination. And this R squared adjusted, you can just ignore that one. That's not one measure that we are going to use. So on the next page, it asks us about that particular context. So for part A, what is the equation of the least squares regression line that describes the relationship between row number and test score? So we can use that computer output from the previous situation context and grab that. So the test score is our response variable. That's what we're trying to predict. We have the y-intercept is 85.706 minus 1.1171. That is our slope from the table. And then the context for our explanatory variable is the row number. For part B, interpreting the slope. So for every one additional row that we move from the front, so we're moving farther back in the classroom, we predict. Again, whenever we are talking about our model, whenever we're making some inference about this particular model, this is a prediction. So our model predicts a student's test score will decrease by 1.17 points. Find the correlation. Correlation is R. Correlation is what is represented by the lowercase r. So what we need to do is we need to take the r squared from that previous computer output and figure out what is the square root of that. Because we're taking a square root, it could either be a positive or a negative original number. So we are going to use whatever sign the slope is. So since this slope is negative, we are going to be using that negative sign as our final answer. So the r squared from the other side, it said that it was 4.7%, so that as a decimal is 0.047. So we take the square root of that, and we end up with negative 0.217. So this is a pretty weak association. Looking at part D, is align the appropriate model for this data? So whenever it asks you about is align an appropriate model, we could be talking about r squared, but it's always better to refer to a scatter plot if you can, or a residual plot. So the scatter plot was just kind of all over the place. The line was not pretty close to all of these, and the residual plot kind of demonstrates that. It's randomly scattered. So because there's no obvious leftover pattern in the residual plot, a linear model is appropriate for the data, but is it a great model? No, it's not a great model. So a line is as appropriate as pretty much anything else. All right, that is part 3 for the 3.2 notes. Have a wonderful day, guys.